Hi everyone, welcome to today's SIG scheduling meeting. Meeting is being recorded, so will be uploaded to YouTube. So be aware of what you are saying. Be respectful to each other. Okay. And today we have two agendas items here. So first one is to give some introduction on the Kubeflux scheduler plugins. And Claudia, if you are ready, I can hand over to you.
Yes, sure.
Yeah, let me see if.
Yeah, I cannot.
Co-host. 1 second.
Mm-hmm.
Yeah, give it a try right now. Let me share my screen. Yeah, can you share your screen now?
I think so.
Yeah.
All right.
Yeah, we can see you. Yeah, we can see your screen.
Great. Oh, well, I have no idea how to go in full screen. Is this maybe? Is this still working? That's the first time I tried that button.
Yes, all good.
All right, great, thanks. Right. Hi everyone, thanks for the opportunity to speak about the scheduler plugin we've been working on. I'm Claudia. I work for IBM Research in New York. I am part of the hybrid cloud infrastructure software team. I mainly do a few things related to Kubernetes topics, and one of these work is Kubeflux. I'm also working in collaboration, so it's not just a one-man band. This is a collaboration with Red Hat. I think Eduardo is here too, and Lawrence Livermore National Laboratories, one of the national lab in California, and they also are the creators and implementers of Flux, but let's get into that. So the reason why we started working on this project is that we want to target more HPC-like scheduling in Kubernetes, and to do that, so we community also, I guess, would agree with that, is the things that desired features that we want to have when we target HPC applications is to have batch or group scheduling, possibly enable topology awareness in the scheduling feature, and also having optimized placement for different workloads within one cluster. That would be a desired feature, and also having different placement algorithms so that the user can decide how to better have a mapping of their application in the cluster. So to target all of those features, so the best, probably not the best, but a good way to do that is to use schedulers that do that for a living. So why don't we use an HPC platform scheduler to do this job for us? And why don't we try to integrate that into Kubernetes as a scheduler plugin? So that's the context. So we implemented Kubeflux. This is based on, so Flux is a framework, and that's the job manager, workflow manager, and job scheduler that is implemented at Livermore. So they run this on their big machines, and that specifically targets HPC workloads. Within this entire framework is a Flux framework has different components, and one of those is the scheduler, and the scheduler name is Fluxion. And we use that specific component in the scheduler plugin as a library, and we use that as a is wrapped into a container that we use as a sidecar to the scheduler plugin pod. Fluxion is a graph-based scheduler, and the entire Flux infrastructure is targets the representation of the resources and representation of the jobs as graphs, and the matching of the workload that wants to be scheduled to the cluster where it wants to be scheduled is basically solving a graph matching problem. And having a graph also gives us for free a topology awareness of the cluster where the workload is going to run. In our case, in this case, of course, talking about the Kubernetes cluster. So at a very high level overview of how the KuFlux plugin is implemented. So we of course make use of the scheduling framework to implement it. And we use the pre-filter and filter extension points. And in the pre-filter extension point, we get the information about the pod that wants to be scheduled, and we map the pod specification into a job specification that is what Flux is able to understand. So we do this mapping from pod spec to job spec, and we ask the sidecar container to give us an allocation for that pod. If the allocation exists, it's possible to allocate the job. We get back a node name, and then we go over. We move on with the filter extension point, and we get the pod allocated and executed. So this is a high-level overview of what happens. We can get into that in more details if needed. I would like to go back to the list of things that we want to enable when we talk about HPC applications on Kubernetes, because with KuFlux, we're trying to address them. So as an exercise, also tried to explain how and why we are able to target those desired features. So first, about batch and groups or group scheduling. So for HPC workloads, having the possibility to see when targeting, when talking about Kubernetes running on Kubernetes cluster, of course. Considering an MPI application for the easiest example. So we know that having that workload seen as a unique, a single unit or group, that's very important because of how an MPI application works. You need to have all the ranks ready before starting, so we all know that. But having the ability to treat that kind of workloads as a single unit is just the starting point. So you have that, but then what you do with that? So within our plugin, we also use the pod group CRD to manage this, the creation of a group of pods. But that's not mandatory in the sense that also pod by pod scheduling is possible, of course. But once you have the group that you want to schedule, also with the scheduler, we can enable some optimization, like placing the group, being aware of the topology of the cluster, and also given the fact that we know how the cluster looks like, we can better pack or spread the workload on top of the cluster. And the user is also able to decide how to place the workload itself. About the topology awareness, so as I mentioned at the beginning, Flux is the resource model is graph-based. So any the cluster where it runs on is defined as a graph, can be more or less detailed. That depends on how the user wants to go in details with the cluster representation. But of course, that cannot be done by hand all the time. So within the plugin, we create a representation of the cluster that is detailed as much as we can, but also has to be generic enough so that it can apply, let's say, to any Kubernetes cluster. Because if we start to go deep into the features of single nodes or how the cluster is, or the entire topology of the cluster, if it's on a single rack, if it's multi-rack, is it multi-cloud. So this can be implemented how in detail to go, but we found that having it's possible and already good enough with what Kubernetes provide to have a graph that enables us to do a better job at scheduling. For instance, when we talk about MPI, so since I mentioned that, I would like to bring this example over. So since also jobs are mapped to graph so that the scheduler can do the graph matching algorithm to do the mapping, the scheduling, sorry. So also jobs are mapped to graph, and this is done internally by Flux, so we don't really have to do anything of that rather than only just doing the translation from the pod spec to the job specification file that Flux understands. And for instance, if we have a workload that is an MPI workload that has 4 ranks and each of them wants 1 core, this gets translated into a like single job that has count of 4 requests of 1 core each. So in this way, we're able to do like this group scheduling, let's say, and that's submitted as a single request to Flux. At the same way, we can also do that as a pod by pod, having instead of count of 4, we have a count of 1, and we have 4 requests of them. Having this, the result would be the same in terms of what the scheduler gives as a result, because it's there is, given the placement algorithm that's chosen, the result would be consistent. But having the possibility to make the entire group as a single request, this also helps optimizing the time that you get the entire location, because instead of having like 4 different requests, you have just 1. So this is an optimization that can help in certain cases, or even having pod by pod, that would be the same. I saw a raised hand.
Yeah, just a quick question on the translation you mentioned between the pod spec to the job spec. Like the scheduler framework is a pod scheduler. How do you translate that to count 4, for example? Like, do you, how does that work? How do you determine the job size?
So for pod by, so let's consider the 2 cases where we have a pod by pod or a group scheduling. For pod by pod is just a single pod, so we get the request, if any, about the CPU, memory, accelerator, whatever it's requested by the pod, and we create a simple basic job spec, is a YAML file, basically YAML format, and that represents the single pod. If instead is a group of them, one not easiest, but the better way, at least in my opinion, but can be I can be wrong, of course, is that by having, when we want to do a group scheduling, having the CRD, that is the pod group, that already has the information of the members of the group. So given that number, we can define the count here. So that is given like for free. If you don't have the pod group, you can like, if the pod is part of the replica set, you know the replica set. So this, you can get that to that information if you want. But yeah, that's also workload dependent. With the pod group is kind of you're abstracting that.
Okay, so I thought that this is already implemented and you already have an opinion, like the kubeflux plugin have an opinion how to define a group of pods as being a single unit of scheduling. But I guess at this point, you still have this model where there's a job controller, whether, for example, MPI operator that actually creates the pods, right? Like, and then you need to look at these pods and identify them as, oh, these pods are related to each other and needs to be scheduled together. You will hold them and not schedule any of them, but create a single resource of kubeflux or Flexon. Sorry, I'm not. Maybe I'm missing the terminology. Job.
Yeah, it's okay. Yeah.
Your system, and then your system will respond to you with scheduling, like which nodes these 4 pods, for example, should land on, and then that's the workflow.
Yeah, yeah. That's about pods. It's not a workflow manager. So the job, even if it's a group, can be treated as a 1-by-1 or all together. So what we do, let's consider this example here where we have a single workload with the 4 pods, and we want to do a single request. So we pack that this is highly simplified, and we request the allocation to the sidecar container. And what we get back can be either like one single node or more nodes. So we get the entire result. We save that information for the pod group. And as the pod arrive, we give a node. We assign a node to that pod, and we go on until we finish all the nodes. So we get the entire allocation, and then we manage and we assign the nodes to the pods as they arrive.
So do you use I'm sorry, I'm drawing blank. What is the extension point where we hold the pods pending?
Reserve.
No,
Permit.
yeah, the permit or or the reserve extension point. Is that...
Right. So that part we can do this before. So we in the pre-filter stage. Let me go back so we have it. Yeah. So we are using those 2 just for Flux. When then it comes to the group scheduling, we also enable the other ones, and we can exploit the co-scheduling extension points. So we kind of combine 2 of them. But the information, the list of the nodes or the node where the pods have to land, they come here in the pre-filter extension point, because here is where the pod arrives first, and we can get the and we ask Flux where to put the node or the group of nodes. So at this point also we get the entire allocation, and then we feel in the filter extension point, that's where we can eventually assign the node to the pod. I don't know if
Is that-
maybe it's a better way to just skip the filter and go in any further extension points. That now I have the doubt.
So it sounds to me you are not leveraging the scheduling framework that much. It's just through the scheduling cycle, you just use that as a hook to invoke your external function
Right.
server, and the function server is doing the heavy work. So my question is that the function work watch all the events related with scheduling so that it can make the good schedule decision. So like does the function, I mean the external function component watches all the pod events, no events, PV, PVC, etc. Anything related with scheduling?
No, it doesn't. It's just a service that runs there and waits for scheduling requests.
But if it doesn't watch those factors, how do you ensure the schedule decision is correct?
Because we so when this scheduler is deployed, we get the entire cluster and we build the resources, the graph of the resources out of that. So
Okay.
whatever is built there, we know that we can match on that graph. And also assuming we have two different workloads that have to be placed, the first one arrives, do the allocation, you get the rest a set of nodes, and you run the first batch of pods. If another one arrives and the previous one is not completed, the resources are still marked as being used. So the Fluxion component knows that those pods are still there and the resources are not free. And once that previous job or any job that was scheduled by Flux is completed, then the resources are being freed. So actually there is a watcher on pods here in the Flux part, but this is not really related to how to enable the scheduling, because that's just to free the resources after the jobs are completed.
A question. So are you saying that your scheduler maintain its own resource resource calculation, resource database?
Correct. Yeah. As of today, that's static in the sense that it's easier to avoid this split brain for the resources if you kind of reserve the nodes to Flux scheduler. So you have a set of nodes that you partition your cluster and you assign that to the scheduler. Is in our plan to make sure that the internal state is kept up to date with whatever else is running on the cluster if the nodes cannot be reserved. So this is on the plan, is not an easy job to do, because it can be quite heavy computationally talking about, computationally speaking, I wanted to say. So the easiest way to solve this problem now is to just partition the cluster and have just one scheduler using one part of the cluster.
Yeah, because I'm thinking if you have your scheduler is running and the Kubernetes scheduler is running, right? Both are running, and then they have different database. That could be very complex, you know.
Exactly. Yeah. Yeah.
So yeah.
That's why we went the easy way for now. Yeah.
So okay. But if your scheduler is running as a plugin, right? My understanding as a plugin to the current Kubernetes scheduling framework.
Mm-hmm.
Is it possible for two schedulers to running at the same time and managing the same cluster resource? If that's the case, and then there could be scheduling conflict, right? Because it's like two brains are making are working to make the decision, looking at the same resource, same cluster resource, right? And you have different database, and the resource might not be synchronized very well because there are two schedulers running in parallel.
Yeah, that's correct. That's a problem. It's like a in one way, if you are the Kubernetes cluster scheduler, you know what resources Flux is scheduling because you see the pods, all the workloads. It's not true for the other way around because of the internal resource representation. That's not a unsolvable problem because you can update at every scheduling cycle as you usually do. You update the node list and you can update. You can see what's actually running and update the internal state of the Flux scheduler. So that's possible to do.
Yeah, but it's, you have to log, right? You want very accurate,
yeah, of course. It's not. Yeah, it's event based, so it cannot be 100%.
Or you have to partition it. Let each partition that's managed by one scheduler. Okay, but anyway, going down this route, I think there are quite some issues that need to be considered. I have another question. It's about the topology aware. So what could you go to your next slide that shows the topology aware? Yeah. So you are topology aware. You go to the GPU core. So you are going to have that nodes, GPU and core layout or topology information in your topology, database or whatever. Do you have that, or just say how many GPU, how many core, how many CPU core, or you have the real topology, hardware topology?
We can get to the real hardware topology. We were doing that with the not feature discovery operator. So we already have some integration with that. So it's possible to go as deep in detail as we want. So if we have the NFT operator that gives us more information about the hardware, we can do that, yes. And the scheduler knows all the things related to the infrastructure and can take advantage of that information. But to keep it easy, actually, yeah, this core maybe CPU was better. To keep it easy, this is the kind of representation that we create by default. So that's what Kubernetes gives you.
Okay, I see. Thank you.
I think Aldo has some questions to ask.
I do, but I think it's better to proceed with the slides.
Oh, yeah, sure. Yeah, I don't have a lot more slides. So yeah, we mentioned this already. So another feature that having a well-oiled machine for scheduling will give you is that they can implement more matching policies. So in this case, there are a few of them, like 4 or 5, if I remember that correctly. More can be plugged, so it's also composable in that perspective. And in this way, we can also enable packing or spreading when doing the scheduling. This has to be selected at startup time. So when you create the scheduler, you have to define that, but that can be also customized and decided at runtime what kind of algorithm you want to do and what kind of allocation you want for your nodes. This can indeed make a difference when you have workloads that are either compute intensive or network intensive. And yeah, also as you can go with the topology specification with the graph, as you can go fine grain or coarse grain, you can do the same thing for the job spec. So you can be very generic, like I want this pod somewhere, or I want a pod at the pod that has exclusive use of a node, exclusive use of few CPUs or these kind of things. Why an optimized placement is a feature that can be very useful. So as if you have a large cluster and you want to like partition the cluster and run different workloads on that cluster, partition in a like soft way, not partitioning the nodes. So just like having a soft partition of the cluster where you want to run, for instance, two molecular dynamic simulation and some other stuff. I'm using an example, but we have also some results for that. LAMPS is a MD simulator, and these are these are network intensive, sorry. And they perform better if the ranks are close to each other. So instead of putting the ranks here and there in the cluster, you would really want to have them close to each other. But if you have two workloads, so you want to pack those into a subset of the nodes so that they don't interfere with each other. And with the pack algorithm, you can do that. We can do that with the scheduler. And so we are doing some performance evaluation of how those workloads work on Kubernetes. So this is very preliminary, so more optimizations can be done, and also we have to learn more about the benchmark itself, LAMPS, to be able to make it run better. So here we are kind of playing with the input parameters, the number of MPI workers, ranks, and how you want to run this. But just as a as is, when we compare in this graph, we compare kubeflux with low node match policy that is doing packing, because we know that LAMPS is network intensive. So we don't want to spread the pods all over. And we compared that with what the default scheduler can do. And so here, this is a cluster with 24 nodes. So you can have like one-to-one mapping up to like here. So then performance can start degrading. But what I want to show is that this is very, naive, but having a better scheduling can make a whole lot of difference in the performance of the application when we also talk about HPC, traditional HPC workloads. Here you see like a 5x improvement. Higher is better in terms of time steps a second. So this is very promising, and we're very enthusiastic about the results. And I think that's, another bunch of use cases. These come from the national labs and more like HPC, traditional HPC workloads.
I have one question regarding your previous graph.
Which one?
This one. I'm wondering if the comparison is fair, because KubeScheduler doesn't know anything about the application, right? So but on the other hand, there are certain APIs in the pod spec that you can use to pack. So I wonder.
I want to touch this point. Absolutely correct. Indeed, we are trying to be as fair as possible, and with the MPI operator. So here, this is an MPI application, and we use the MPI operator to deploy it. And this is the, as far as we got with the testing, this is the best that we get so far. Configuration of workers, MPI ranks per worker. So there is this slot per worker configuration that you can set in the MPI job spec. And also we tune the npm run command so that it's doing the mapping of the ranks per node, so that it's trying to do its best to
Right,
put
sorry,
the,
but those are application level things. I'm wondering more of a scheduling configurations, for example, using pod affinities to suggest the scheduler that the pods should be closer in the same topology, using node affinities and so on.
okay, yeah,
so
we didn't try that. We were focusing more on tuning the application regardless of the scheduler. So those are optimization that a HPC person would do to run on bare metal, regardless of the scheduler. But yeah, you definitely have a point. We have to investigate also on that side. That's very preliminary. I collected this data yesterday evening.
Right, so because if you don't set any configurations at all, then the scheduler will, yes, the default scheduler will spread in all places. So it's not fair because you're not setting the expectations in using the already existing APIs.
Yeah, I totally agree. You have a point. Yeah, we have to test that and see how it goes. Absolutely. I think I took all the time.
So I have another question. So I'm also very concerned with the architecture you have, because you have basically two schedulers. So I wonder, why didn't you consider just to run your own scheduler entirely instead of having these two states? And I'm not really sure. So there is another project that is within this SIG. It's called the cost scheduling plugin. It's not it's not in core Kubernetes. It's a project, and it actually runs using the framework and not splitting the work into places. So I wonder if you investigated that route, and if you plan to merge those, or on the other hand, whether you just consider writing an entirely new scheduler, which is what other platforms are doing, like Volcano, for example. So there are streams, right? And this seems like a weird middle place that I just want to know what's the advantage of this one, this architecture.
Right. So the advantage is that having exploiting a HPC scheduler, an existing one, is that the HPC community knows better how to do these things. So it might be or might not be a good way of porting that knowledge into this field by exploiting what they did. So it's like, let's not reinvent the wheel, but let's use their wheels. So that's a reason. I get also, so the comparison with the cost scheduler is not completely fair, because those are solving two different problems. But I get what you're saying, meaning that why don't you implement the entire algorithm within the plugin, for the same reason as there is an existing thing that we can use. This, of course, introduces other problems like this double resource state. But I mean, that's probably the price to pay for this specific case. So that's the route that we decided to take.
Yeah, I think one thing to evaluate is to evaluate the overhead that your plugin hook call the external fluxation gRPC service, how the overhead looks like.
Oh, it's a
Because I think-
millisecond. Sorry, go ahead.
Yeah,
Sorry.
yeah, I think because it's a blocking operation, and if that overhead is too much latency, I think it will be more good to incorporate, sort of migrate your function internal data structure into the scheduling plugin itself. Then you do everything in the memory instead of calling external gRPC service. Yeah, I think it's good to evaluate the performance.
Right. So with the one with the gRPC is like the second version. We implemented one where everything was in the same container. So there was no gRPC in between. There's really no difference. We're talking about milliseconds. So that's definitely something that we took into consideration. It's TCP now. Another optimization that can be done is to move that to mixed domain sockets. We didn't do that yet, but that's in the plan. But really, it's not introducing any latency. We've been measuring the startup time and the scheduling time between the two, like kubescheduler and kubeflux, and there is really no difference.
I think, maintaining two resource database is not a small overhead, and how to make sure these two databases, the resources are in sync. That's another issue, right?
That I agree indeed. So we also had discussions about that with our Red Hat counterpart, and like asking how would you solve this problem, or does it make sense to solve the problem? And the feedback that we had is that having the cluster partition and having like nodes reserved to this kind of workloads, that would be definitely the preferred way. So that's also why we're sticking to the this reserving nodes to the specific scheduler.
Yeah, but if you have like partition, right? You have each partition has its dedicated scheduler. Then it's not optimal, resource optimal, right? Because one partition may run out of resource, but the other partition, there's still resource in the other partition, but you cannot use that scheduler.
Right. Yeah. Absolutely. Yeah. But this depends, I guess, on the how you need to use the cluster, because this, of course, there might be occasions where you run out of resources in one and you would really like to have more resources and stealing them from the other subset of nodes. But if you are dividing the nodes into 2 or more groups and you want a certain set of applications to run there, and to have that number of nodes just for yourself, then this is I think acceptable. But this depends on cluster admin and all that stuff, I guess.
I want to close.
Yeah, I think we almost are run off the time. Yeah, any further discussion we can have those happen in the community Slack or in the mailing list. Yeah, Claudia, does that sound good to you?
Absolutely, yeah.
All right. One quick note. I don't know, you might be aware of the working group batch that we created. So I think we could also continue the discussion there. What you said, like don't reinvent the wheel, is something we definitely want to encourage. But this architecture, it needs to be discussed further. If we want to have a single solution for HPC, definitely we want the knowledge of the HPC community. So we need to find a good way of attaching this knowledge into perhaps the existing instead of trying to partition the decision making. So yeah, maybe we can have another session in the working group.
Sure.
And there we also have people working in topology for the nodes specifically, so that could be a good thing to discuss there too.
Yeah, thank you, Claudia, for coming up with
thanks,
this.
everyone.
Yeah, thank you. So the next item I want to mention is that I haven't created an issue yet, but this is pod resource metric that was introduced in 121 by Clayton. So basically the background is that different components may compute the pod request differently. Like some code buggy, like doesn't take the init containers requirement into consideration or calculating the wrong way. And some component, like yesterday I checked the metric of the kubestate metrics, they just iterated the regular containers add them. So that's not correct, because you have to consider init container and consider the pod overhead. So what Clayton wants to propose is to have a source of the truth view of the pod request among all the Kubernetes components. So that's pretty good. So yeah, I'm really like it. So that we can use this metric to come up with aggregated usage on node per the aggregated pod request. So, but problem here is that yesterday a colleague came to me to say that the cardinality is pretty large, especially the pod dimension. So because this is a multiplying relationship. So in a large cluster, if you have 4,000, 5,000 nodes, and each node has like 50 or 100 pods, this is a huge multiplier. So this makes the Prometheus scraper a large pressure, even one single time to scrape the metric. So I'm considering, so basically, I don't see that a metric involves a pod level. So it's basically a high level metrics. And I think namespace, node, priority are all good. It's just that the pod level is too low level. So I do want to eliminate the pod dimension. So I want to, yeah, see how do you think?
Sorry, but what information do you want? Do you just want the usage?
I don't want to remove the pod. Yeah.
Right. So in that case, you would only have the information for how many resources are being used in a node.
Yes.
And I guess that was not the initial intention of this.
Yeah.
This
So
metric.
I'm not sure if I'm not sure if I missed something in the original CAB discussion, but right now it seems impractical. The pod dimension is too low and it causes too much pressure on the Prometheus scraping. Yeah.
And Clayton's defense was that this is, well, for once it's not maintained in memory, so you only the scraper would pay the cost, not kubescheduler. But I think the need is to actually know how many resources one pod is using, and if you don't have the pod label, then there is no point.
No, it's not a pod label. It's just a pod name, I think.
Yeah, label as
okay, label for the metric. Okay.
Yeah. So I think this is the intention. So not sure if you can get around it. That's
yeah. I can talk to Clayton on this. So basically, it's just impractical, not that ideal. Because if you're troubleshooting some performance problem, usually just the metric gives you a high level overview on this. So if you want to pinpoint the specific part, usually using the metric is not the standard way to do that. Yeah, that's why I don't want to have the pod in the metric level. Yeah, just want to raise up this. Other than that, I think there's no agenda item in today's meeting. But if you do have any questions, you can raise it up. If not, I will close today's meeting. And I want to mention that Abdullah raised the regular meeting from 30 minutes to 15 minutes, 55 minutes. So basically, that's still be the rule for regular meetings. Yeah, we can accommodate more items in the future. All right.